Cool. So this is my second attempt to record this video. I basically had to trash the other one because I realized that I was in pause. And I was just talking, and it's a PD. I mean, I think you probably didn't lose a lot. So I was doing basically two things. I was going through, so I talked a little bit about these ansatz in here and what I want to do with it. So I want to basically try to kind of hack into it a little bit, try to, play with it, see what happens. Because what I kind of came to realize is that really what this is doing, right? This ansatz. So let's recall this a little bit. That was what I was talking now in the video that I just trashed. So if you have a matrix of your coefficients of your linear system of equations, it's this one, and then you have the ket x, which is the vector that encodes that holds your variables in the system of equations, and then you have the ket b that kind of has the right hand side of your system of equations. All what this is doing is trying to approximate these, right? Not approximate. It's trying to come up with it generates one of these, right? And so what you're doing with the Hadamard test, in theory, is extracting a certain property that allows you to basically calculate. I don't know if it allows you to calculate directly that, or it allows you to kind of work towards this equality in here. Because the idea is, if you think of these two terms being vectors, and I shouldn't do this on my camera, but this is b, right? This is b, and if we call this whole thing, this phi thing, or is it, I don't know what is this later, but so whatever these is, right? What you want to the quality, or let's put it this way, the similarity between these and b's can be determined by the projection, by the like if you project those vectors, how closely they are. Because if they're the same vector, then the projection is like basically maximum. If they are perpendicular completely, then the projection is minimal, right? So you want your cost function to be designed this way. But we're going to put this aside for now, and I want to play with these. I want to play with these and see how. So what interference patterns those control Zs generate in conjunction with these Y rotations. And what I did in the video before is I went through this tutorial quickly. And this basically, the circuit is a bit different, but I think essentially it's the same. I don't really understand what is this. Those A sub L's are just the decomposition of A, right? Because A can be any kind of matrix, and you want something that you can simply stuff into or plug into a quantum circuit. And so, all these numerals, it has to make sense. It has to be constructible somehow. That's my point. And so the whole tutorial here goes on saying, hey, let's assume that U is just a where's that? Here. So let's assume that do an example. This is how we can decompose A. So this is really our A, and this is really our U. So it's just a bunch of Hadamards. And here they use a simpler ansatz, just a one layer of rotations. But there's no really intuitive explanation of why the Hadamard test tells you or gives you what you need, right? If we take a look at the Wikipedia, that's basically the same kind of demonstration about being the expectation value and stuff like that. So I want to play with this a little bit. How much time do I have? Not much. Anyway, let's open Quirk. Let's clean that up first, so I can see things better. I'm gonna move that into my secondary screen if I can. Yeah, so I can basically now go in here and say, so we got like Y rotations, okay? So what I'm gonna do is I'm gonna just, can I not? So I just wanna do, instead of making these a parameterized, so I will, sorry, it's parameterized by, as a function of time, I'll just parameterize this with pi, okay? And I think I should be able to do like this, basically. And now, okay, whatever. No, I don't want the minus, I want the, okay. So I'm just gonna copy the layers 3 times, and I'm gonna use the same pi, because in theory each of them could have a different parameter, right? But the control sets are not parameterized, so they're just like these. Control Z, and the other one is like these here. Okay, cool. I think there we go. Cancel. I'm gonna move the whole. Yeah. Okay. Cool. So the whole column goes in here. I don't want to change that. Okay. Cool. So that's interesting. So that actually turns the whole thing into 111. So it's basically that's interesting. So this basically does nothing to it. Oh no, this actually, okay, yeah, that's pi, of course. I wanted to do pi divided by 2. That's what I wanted to do. Let me update that quickly. So pi divided by 2. Pi divided by 2. 2 pi divided by 2. Pi divided by 2. Pi divided by 2. Pi divided by 2. Okay, interesting. So this is giving us a particular superposition. Where am I? So this is basically telling us, so this is 110. Okay, interesting. So this kind of creates the equal superposition. So that's like all Hadamard's. That, of course, changes the phase of 2 particular elements, right? Namely this and this element. And so here's where interference happens, right? Because now, yeah, so now this doesn't go back to 0, 0, but it kind of goes here. Interesting. Now, this does also affect or also change the. It's 2 layers, okay, but it's. I'm kind of like, it's probably a run. I don't know. Is it the random decision what control Z gates you're using in here? This is qubit 0 and 1, 1, 0, 1, and then 2, 0, and this is 1, 2, 2, 0 again. Because in this case, that's affecting only one phase. Yeah, but that's kind of creating the interference, right? So it's a bit of a, so those interference patterns are, those control sets in conjunction with these. So here's where the interference is triggered, okay? I wonder how this changes if I just go here and say that's pi thirds, right? Okay, so those things are just a little bit less rotated, but the effect is kind of the same. So here you've got a bit of a different final state. So if I turn those into, if I change these by like a time-dependent one, just these. What you can see is that I'm exploring different, so those are different states in here. Interesting. Well, this is always empty. If I do it here, it's kind of the same. So this layer, okay, so and now it's like that. If I make them all dynamic, that's the way this looks like. So it's still ignoring some patterns in here. I want a lot of variability in here because that's what you want to do, is you want to explore as many possible states. And I also want to have moments where I have entangled states, because those are, I guess, what makes it unique in terms of it being quantum. If I am forgetting, how do you select? It works like this, but why doesn't this work with the, yeah, okay, no. If I put this layer here and I put this layer here, so the one that I'm varying is only the one in the middle. Then I'm getting all this stuff. Interesting. You're all varying at the same pace, right? If I vary this one, sorry, slower. Is it slower? Okay, it's a bit different. So I don't want minus pi. It's just control what I have to apply. Okay. If I, so let me go back to pi divided by 2, pi divided by 2. All fine. I mean, like, I don't know, I don't think there's anything really crazy interesting for us to figure out exploring this. What I'm interested to see is what can I find with a Hadamard test by just doing the Hadamard test the way that is explained in here. Sorry, it's in my secondary screen, which is basically, I'll just copy paste the URL so I also keep it there. Where's the Hadamard test? The Hadamard test is here. Here you go. The reason why we're applying two different gate types is because this presents the pairs of gates shown in the expanded form. So we can use two levels have to compute, starting with okay, so the Hadamard test. A nifty little quantum subroutine called the Hadamard test allows us to do this. Essentially, if you have some unitary u and some state, fine, we want to find the expectation value of u with respect to the state, yeah, after applying u. Then we can evaluate the following circuit. Then the probability of measuring the first qubit to be 0 is equal to these, and the probability of measuring 1 is equal to these. So subtracting the two probabilities gives us the real part of u. Luckily, the matrices, we be dealing with when we test this algorithm are completely real. For this specific condition here, okay, here's how the Hallmark test works. By the circuit diagram we have, so by the circuit diagram we have as our general state vector these, yeah, applying our controlled unitary. So the idea is kind of basically, you only apply unitary in the portion of your state vector where the control is 1. That makes sense. And then by applying the Hadamard gate to the first qubit, these minus these. So this turns into this thing. We take the measurement of the first qubit. Remember that in order to find the probability of measuring 0, we must take the inner product of the state vector with 0, multiply its complex conjugate. Okay, yeah, so then they just calculate like this and they say, okay, here you go. This is this. So that's just the math. Is there an intuitive way to understand this? That's what I'm trying to figure out. Why is that? Like the problem, the problem that I have with this is that they just go ahead and they say, bam, here you have the explanation of the quantum of the Hadamard test. And by the way, yeah, you just do it with the control Z. So why Z? And why qubit 3? That's what pisses me off. That's what pisses me off. We're applying 2 different gate types. Why 2 different gate types? Isn't there a representation? Well, concern with that, and I get so. There's a sophisticated way of solving these for solving this for this value using a newly proposed subroutine called the Hadamard overlap test. So this I definitely want to investigate as well, Hadamard overlap test. But for this tutorial, we'll be using a standard Hadamard test where we control each matrix. But what matrices are we? Creates controlled ansatz for calculating so you're controlling every single gate. It's just confusing. That's confusing. You're creating a controlled fixed ansatz, but why? What the hell is this? Hadamard test. So you're actually having 2 circuits. So one is used to calculate the control fixed. So one is used to calculate whatever thing else you were trying to calculate, and you're calculating it by controlling the ansatz. And that's basically what the penny lane people are doing here. They don't even control the ansatz. Come on, that's the ansatz. It's not controlled. Only A is controlled. They don't even explain what's these people. Come on. So what do you get? Let's try to understand this. Okay, so I think I'm gonna end up doing another video just on this, to be honest. What? Just checking the time. It's a bit late over here. So let me clean this up for a second, and then let's see. The Hadamard test. Okay. And I'm gonna move this whole thing here. And so measuring this qubit is going to supposed to be telling us something. So we have pi halves everywhere. Isn't there a way that I can parameterize that rotation anyhow else in Quark? Maybe I can do those rotates target by input. Because maybe I can, if I use these, I think I could use that. I think I can use those gates. Let me play with something. So no, I keep the hardware. Trash these. Trash these. So I want to use these, and I want to have an A here and a B here. Okay, and so need input A. Doesn't it have the input A, or what are you complaining about? What are you complaining about? Oh, I think they need a. Oh, they need A like these. Ah, okay. Because I think like that I can basically do. Now I can basically do. That's a pretty cool feature, but it needs input A. So I can actually do it like these. Okay, so it's gonna make the circuit here big, but at the end of the day, I just care about that qubit in here. So we're gonna put a block sphere. That's the first thing, and we're gonna put a chance display in here. I mean, you can't do that with any other visual tool. I'm sorry, but it's yeah. So we can kind of create here. Just define 4 values. Like if I define like this is 1, right? So this is a so if I do 1 0, that's basically a pi. So this allows me to define. That's really cool. This by using 2 qubits allows me to define 4 values. So this means that like 0 means 0, 0 1 means pi halves, 1 0 means pi. 1 1 means pi for 3 times by something like this. Yeah. Exactly. So that's good. Oh, and now if I'm smart and I don't want to keep typing these in here, I think I can even use those things in here. Sorry. So if I change that to A being like 2, that doesn't change anything, right? It doesn't work like these. Doesn't work either. Okay, I don't know how to use that. Doesn't matter. It's just use default values, I guess. But if I set, so if I set, for example, those to be like all 2, right? So that's where we had, that's when we had these, oh, I should definitely save these, bookmark these, workspace. That's the ansatz VQLS test 1. So, and here I'm reading 50%. Okay, should write this down maybe somewhere. 50%, 50%. So 50%. But why I'm doing a Z? Like, how does these? I think here and like that's a. And why this damn qubit? I mean, that's I just still don't damn understand that. Not that. So, it's, to be honest, a bit daunting because I don't know where to start. Like if I do these now adding a bit of a different rotation, I keep seeing that it's 50. It doesn't change anything. Okay, now it changed. What happened? 62%. And it, to be honest, it seems like, okay, so it seems like the only thing this is doing is copying that qubit, the probability of that qubit. Like if you do a Hadamard test with a single Z gate, that's what you're doing is are you just are you just cloning, not cloning, but like you're copy, yeah, kind of cloning the, because basically what you're saying is so whatever state you're in, right? Let's assume you're in the plus state. Kind of go, you apply. Trying to think conventionally, to be honest. And so for the part that's 0, nothing happens, and you still stay in the plus state. For the part that is 1 in these, that's kind of because of the Hadamard in here. Then go to minus, right? And then, and so, what? So when you apply Hadamard again here, then kind of like, what is this gonna be the measure, right? So if I keep back to this being like 0, that's where we were, right? So, because now it's like, okay, but I don't know if it's in the plastic because that's totally entangled. But let's assume that's the case. And when I measure this guy over here, how many times I'll measure 0, how many times I'll measure 1? It's basically similar to what I'll measure here, right? is it? It's funny because so you're actually, what you're doing with this particular construction is you're basically saying for the part that is 1, just apply a phase shift. So you're actually differentiating. You're actually differentiating these. Something tells me it's literally cloning. Like, so if I have, like, I don't know, let's do these, right? So I have these state. I'm gonna add just for the sake of separating things. This is just a dummy cable. So and the actual test is here, right? So, and I'm gonna actually add more dummies in here. And if I have a block sphere, yeah, that's entangled. It's copying the probability. If I apply a Z gate, or if I apply, okay, so let's apply a, so it's copying the 1, the plus is entangled, minus is entangled, I is entangled, all this kind of stuff is entangled. But if I, for example, apply a Y rising gate, this is literally copying. This is just copying the probability. Okay. No matter what I do, if I do a next rising gate, it's copying. That's just it's a useful trick. Okay, so you're copying the probability. That should be something to remember. That's definitely something to remember. So you're copying the probabilities. I'd like to break this down, but I probably should do this in another. Is this the Hadamard test? Is this? I guess it's an application of the Hadamard test. Yeah, you're copying the probabilities really. If I why is that you're copying the probabilities? So if I do an X quarter, if I do an X quarter, right? So what's happening here? You have an X quarter. And so for the part that is for the part that we're 0 and the part that we're 1, right? So this kind of stays as is, right? But for the part that's 0, okay, so if we, maybe I can take a look at, what if I pause select on 0? And I take a look at the block sphere down here. What is this block sphere doing? Is it pointing up? But it's a bit entangled. What is that? No, it's totally 0. Okay. No, but it's not. It's like there's a bit of entanglement. Why? if I pause select in 1, hmm, hmm. So the point is, for the part that is 0, right, it stays like that. For the part that is okay, so it creates, the part that is 1, it creates the mirror state because it applies a Z. It creates a mirror state. And so it creates a mirror state. And how do I determine intuitively the probabilities of measuring 0 or 1 in here? Is I've entangled these two things. And so basically these two states are literally orthogonal as well. So am I right to say whatever probability distribution this generates is kind of going to be copied up here? It feels like you're splitting the thing, right? You're creating, that's nice. You're creating, we'll try to go back to why this is useful there, but you're creating how to say these? Because you split kind of you got into superposition, and now only in one branch you actually apply Control Z. Like the probabilities of measuring 0 is going to be the same probabilities that you've got down here of measuring, of kind of like measuring the state, right? Versus, which is like 14%. I don't know. I think I get it, but effectively it's copying the probabilities. Okay, so what it's doing, it's basically like by utilizing a superposition. I don't know. I feel there's something else in here that could be useful, but I have to come back to it later, I guess. I'm all in all, how much time have I been now recording? So about 40 minutes. Don't want to make the videos too long either for you guys, but like, so okay, so what this is doing is literally copying this probability in here. And the question is, why would these be representative, or why is it something that is useful? Here. Okay, it's calculating that was to calculate the project. No, that's to calculate these. Is it? Yeah, that's these. What we're trying to calculate is these. Starting these. What is these? Let's try to go back to what is this symbol. I mean, that is the, okay, so that is the, okay, so that's these. That's that part. Mm. And why are we trying to calculate that? Because it's part of our cost function. Why? Because we're projecting. How much of these lies along these? Now we subtract from the number. Small norm, then the cost function will still be low, even if it does not agree with P. Thus we replace these with these. Okay, so this is our cost function, and the idea is, okay, so that's what you need to calculate in here. So I've prepared our state with the answers. Now we have two values calculated in order to validate the cost functions. What is the intuition behind? That's what I okay. So that's what I have to try to find. Now I figured it out. So it's trying to. Okay, but why is the latest qubit? That's kind of the question that I have to answer. Why is it only applying to the latest qubit? That's what I don't get. So this is somehow trying to get that component of the whole. Why the last qubit? That's what I don't get. What is it in here that is so representative of that state? So this is 0, 1, 1, 0, and we got 50%. If we do these, so if I do this rotation with a 2 and a 3 here, then I get 67%, 62%. 89% with these rotations. What does this 89% kind of represent? Like, how does this represent anyhow that? Because remember that these here is the x, right? But for some reason, we're trying to extract something from the last qubit, and I don't know why. I don't know why this is just anchored in the last qubit, or in the qubit Q3. That would be right, because that would be Q2, because that would be Q0, Q1, Q2. I mean Q3 if we count this as Q0, but I'm not gonna count this as Q0. So we're doing rotations. We're doing this kind of stuff in here. What if we move these here? Okay, those are definitely different, right? Why is it that I'm interested in the last one? Okay, and that's probably a question for next for next video. Yeah, that's not gonna be. I'm not gonna get too much out of this today, but at least I've built a basis to explore. So I've built a basis to explore here the way the ansatz works. Maybe I should simplify that. What if I had like a simpler version of these, where it's like just one layer. So let's take the example of just one layer, right? And let's have two separate. Why would that? Why that? That still doesn't make sense. Why that qubit? That's something that I can't. Maybe it's a mistake. Is it? Harmer test. Grid Harmer test. So here it says, sorry, I should be looking at these so you can see it in the camera. Here it says, Hadamard and Sille index. Apply the fixed ansatz for IE in range 0 is the gate type. If gate type equals 1, then do a control Z. Okay. So there's something off in here. What are the gate types? You're kidding me. So gate type, what is 000? Qubits 001. Oh no, wait a second. Gate type is the whole thing. Qubits. Gate type is these, okay. Ah, okay, I get it. I get it. This is just a generator block. For this beast in here, is it? No. Where is these used? Oh, come on. Okay. Okay. Just go. Because I was like, why that qubit? Why is that anyhow representative? That is the way you, that is just to create the control. That is just the mechanism to create the controlled ansatz, is it? Hadamard test parameters. We're doing a Hadamard test. No, this is the control. This is the controlled ansatz. That's the beast. It's like, this is the controlled ansatz. And so what the heck is this? I don't know. So you're doing controlled, you're doing a Hadamard test, and you're doing for each in range 0 to the gate type. The gate type is 1. If the gate type is 1, what is gate type? So this is seems to apply to the 3 qubits, but then there's this support for this gate type thing in here. Which basically makes it only apply once. So the index qubits IE. So it goes through all the qubits. So this is a map of where to apply these. Just go to hell, man. Why it says This is a map of where to apply things, is it? If I try these, run. Waiting for kernel. Should I have run everything else? Probably. Come on, run. Run. Fixed nonsense. And run. And if I say 1, mi amigo. If I say 1, why is that okay type? Why is that applied twice though? I don't get it. And how is this hardware test applied then? Special hardware test, no. Hardware test, gate set, gate set, gate set. Zero parameters. Gate set, gate set. Where's this gate set coming from? Where's this gate set coming from? The brightness of this. I can't believe this. Where is this gate set coming from? Coefficient set, gate set. Just set it like that because, hey, why not? It's cool, right? So they just come out with a gate set like this. Gate set, where it come from? Whatever. Okay, so I gotta dig into this a bit more. But now I understand this is not a specific thing. Like it just lost like an hour for these, but whatever. This is not a specific. It just copies the probability, but it's not a specific. What happens if I do? What happens if I combine some of those, right? So, for example, let's say you have another control here, right? Another control here, and now you say, come on, let's add this here, and let's add this here. So it's doing some sort of combination of those, okay. Yeah, this is doing some sort of extraction, some sort of phase estimation or whatever. Like, yeah. And if I do this like, then it's totally off. For that particular, come on. Well, yeah, I've basically uncomputed it, but but then why would these, for God's sake, be explained like that? It's just awful. Maybe it's because I didn't read, but could also be. Anyways, okay, so we got something to play with at least. Yeah, but now we understand the Hadamard. This is not done like that. Okay, so there's some extraction going on here. And then there is, now I understand at least that there's some extraction going on here. And then there's this beast, this other component that is the controlled fixed ansatz. And so that's a controlled ansatz. But we're doing two things. So we're controlling the ansatz. And if I compare it to this guy here, they're controlling A, not the ansatz. The ansatz is here and is now controlled. Is this a different approach? Okay, anyway. But it's at the end of the day, it's the same idea, right? Like it's VQE, right? So at the end of the day, it's VQE. But I'm curious to see. I think there's a lot to learn from those kind of techniques on how to extract certain things. It's just because I think it's curious. What is it really extracting? Somewhat the face is somewhat. It's in theory, according to these, it's calculating like these, whatever that is. That's what I need to figure out. That's what I need to figure out. Because that gives me that value in theory. Maybe I need to take a look at the code more carefully, see how that is actually used in here. Because then they do that, and they do some sums and multiplications and whatnot. And yeah. Cool. Okay, but we're getting somewhere. At least I figure out why this is built the way this is built. Yeah. Stay tuned for more, people.